Okie dokie, I'm going to go over some GCSE Combined Science core practicals. Now, these core practicals come up as 6-mark questions, and this is specifically for Edexcel in terms of what paper these particular core practicals are going to be on. But these core practicals will come up for any exam board, because all exam boards, they all teach the same content. Just check and see which particular paper these topics might pop up on for you. So what you might get asked about on paper 1 for Edexcel is investigating acceleration, investigating waves, and investigating refraction. On paper 2, you'll get asked about investigating resistance, a couple of parts for that, investigating densities, investigating water, so that's specific heat capacity, and investigating springs. So the first one, investigating acceleration of a trolley. And this particular question is investigating the effect of mass on the acceleration. So if I just show you the questions here, and then I'll go over the answers in a little bit. So pause the video if you're wanting to try these questions before I start going over the answers. And here are the answers. So the first thing they wanted you to do was complete the table calculating the acceleration. Now this is only an example of the type of questions you might get asked. So you can see the mass starts at 200 and goes down to 800. Now you needed to calculate the acceleration. So acceleration equals change in the velocity divided by the time taken. So there's the change in the velocity and there's the time taken. So for example, to get the 3.18, you just did the 7 divided by 2.2. For this one, you do 6.7 divided by the 2.4, 6.8 divided by 2.8, and 6.9 divided by 3. And then it asks, describe the conclusion that can be drawn from this experiment. So as you can see, as the mass increases, the acceleration decreases. Identify Newton's law that can be referred to in verifying results for this experiment. So that would be Newton's second law, which is force equals mass times by acceleration. Explain why it was necessary to use 2 light gates when measuring acceleration in this experiment. So we need to calculate the change in velocity, which is the final velocity take away the initial velocity. So the first light gate tells us the initial velocity, and the second light gate tells us the final velocity. Design an experiment to investigate how the gradient of the slope affects acceleration. So the gradient is just how steep the slope is. So first tell the examiner what equipment you'll use, such as a ramp, a trolley, stopwatch, 2 light gates, a pulley, masses and string. And your method will be something like this. Use the same method as how they've done it there, but make the board slope downwards by putting books under the board at one end. So for example, they just had the ramp in a straight line. What we need to do is make the ramp by propping it up at one side with, let's say, some books, and then you're going to let the trolley just roll down like that. Make sure you mention a fair test, so release the trolley from the same place each time. Perhaps draw a line on the ramp and make the front wheel, put the front wheel on the line each time. Get the same person to release the trolley at the same time as starting the stopwatch to reduce human error. So remember, human error is about 0.25 seconds. So if you've got one person releasing the trolley and one person starting the stopwatch, you're going to have human error. So to minimise that, get the same person to release it. Stop the stopwatch when the front wheel goes over a line at the end each time. So you could put a line there. So start the stopwatch when you release it, when it goes over the first line, and stop the stopwatch as the front wheel goes over the second line. Use the same trolley each time with the same mass. Last time they were changing the mass, but this time we are changing the slope, theta. Use the same pull force each time, using a mass on a pulley system hanging over the edge of a desk. So, just like that. And this weight here would produce the pull force, so that's the same pull force each time. To be honest, that is a better answer when you were talking about the mass. You probably don't need to do that because the slope will actually pull the trolley down. The second investigation is investigating waves. Pause the video if you'd like to have a look at the questions and try it yourself before I go over the answers. And here's the answers. Identify two equations to calculate speed. So we've got the good old speed equals distance divided by time equation. And specifically for waves, we've got the wave equation, which is wave speed equals frequency times by wavelength. You'll often see it wrote as V equals F times by lambda. Identify a control when using a ripple tank. Well, you want the same light source and it's got to be the same distance from the ripple tank each time. Otherwise that'll affect the shadows on the screen. Describe how you can calculate the frequency of waves using a ripple tank for 2 marks. Count how many waves are produced in 10 seconds, then divide by 10 to work out how many waves there are in 1 second. And remember, that's what frequency is. It's the number of waves per second. Now that is also a way to increase the accuracy, because it's quite hard, or very hard, trying to count 1 wave. It'll be 10 times faster than trying to count 10 waves. Describe how you can work out the wavelength of a wave for 2 marks. Count how many waves there are in 80 centimetres, because that's the length that they've quoted. Then divide 80 centimetres by the number of waves. So the wavelength is the distance from peak to peak, remember? So if this was 80 centimetres, and you can see we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 waves. So you do 80 centimetres divided by 19 waves, and that would tell you the length of 1 wave. So that would be 4.2 centimetres in this particular example. Explain how the investigation can be improved. Well, you could take a photo of the waves with a ruler in the picture so you can easily measure the wavelength. And the frequency, measure the number of waves in 10 seconds, then divide by 10. So as I've said before, trying to get how many waves there are in 1 second would be very tricky. So if you get how many waves there are in 10 seconds, then simply divide it by 10, then that'll tell you how many waves you've got per second, which is the frequency. Describe a method to calculate the speed of sound of an echo. 3 marks. So tell the examiner what equipment you'd use, plus what measurements you'd take. So for example, Say use a trundle wheel to measure the distance, and use a stopwatch to measure the time, and perhaps a clacker board to actually make the sound. All that a clacker board is two bits of wood that you clack together. Say how to use the measurements. So use speed equals distance divided by time. You'll get a mark for that. And the rough method, clack the sound board, time how long it takes for a sound to echo back to you. So you'd start the stopwatch when you hear the first bang or the first clack, then you'd stop the stopwatch when you hear the echo. Make the distance large so that the time is large, so it's easy to start and stop the stopwatch. Very often what they'll do is they'll show you the person standing pretty close to the wall. Let's just say 50 metres. Now speed travels at about 330 metres a second, so that's not going to take long at all. So that's going to be really hard to start the stopwatch and then immediately stop the stopwatch when you hear the echo. If you make the distance a lot further, let's say 200 metres, then that'll give you a lot more time to start the stopwatch and then to stop it. And remember, the distance that the wave's travelling is not 200 metres, it will be 400, because the wave has to go to the wall and then back again. And an example of a calculation, the frequency of a sound wave is 2 kilohertz, so remember that's 2000 hertz, and travels in air at 330 meters per second, so that's the speed. Calculate the wavelength. So wavelength equals the velocity divided by the frequency. So there's your velocity, there's your frequency, and it comes out as 0.165. So what I did there was I just rearranged the equation. So V equals F lambda, so therefore the wavelength would be V over F. And here's the next core practical. Pause the video if you'd like to have a go before I show you the answers. And remember, this is just an example of the type of questions you might get for this particular core practical. And here are the answers. So investigating refraction. Define refraction. Well, refraction is when waves change direction. At a boundary, when waves bend. So remember, if there's a change in density that the wave's travelling through, then there'll be a change in speed. And unless the wave enters along the normal, which means goes straight into a material at 90 degrees, the wave will bend and change direction. Like that. Describe a method to investigate refraction using a glass block, ray box and a protractor. 4 marks. Tell the examiner, use a ray box to shine a beam of light into a glass block. Note the angle of incidence between the normal and the incident ray. So if this is the glass block and we're shining the light in, there's a little normal line, which is an imaginary line which is perpendicular to the boundary. And what will happen is the wave will bend, and because the wave goes slower, it'll actually bend toward the normal. So where I've said here, note the angle of incidence between the normal and the incident ray, that angle would be there. So this is the incident ray. And this is the normal. Then note the angle of refraction between the normal and the refracted ray. So this ray here gets called the refracted ray. And the angle of refraction would be in there, R. Compare the angle of incidence to the angle of refraction and repeat, if needed, by moving the ray box to increase the angle of incidence to see the effect on the angle of refraction. So in other words, take the ray box and pull it over here so the ray would shine in here at a bigger angle. I'll just delete that just so it's not confusing. Using the data in the table, describe the results. So the angle of incidence is getting bigger and bigger, and the angle of refraction is also getting bigger. And you can see that the angle of refraction is always slightly smaller than the corresponding angle of incidence. So 3 is smaller than 5, 7 is smaller than 10, 10 is smaller than 15, and 15 is smaller than 20. So as I gets bigger, R gets bigger, and I is always bigger than the corresponding R value. Explain what conclusion you can make from the data in the table. So, as the light enters the glass, it must slow down because glass is more dense than air and it bends toward the normal. Now with my students, and I don't think I've ever saw this before, so I think I've made it up, unless I'm just making that up. But if that's your glass block, if this is air, so it's a gas and the particles are spread out, and then this is glass, which is a solid, so the particles are closer together. Now, when the light goes from the air, it's travelling fast, but when it hits the glass, it travels slower. Put the normal in. So as the light goes into the glass, it travels slower. And if it goes slower, you move toward the normal. So instead of coming over here, it's going to bend, it's going to swing in toward the normal. Now don't go right over like that. You've got to make sure that you can see a bit of an angle in here. So remember, that angle there is called I, the angle of incidence, because this ray here is the incident ray. And this angle here is called R, because this is the refracted ray. Now as the light emerges from the glass, it's going to go from a solid into a gas, so it's going to go faster. It's like walking through a crowd. If there's lots of people in your way, you go slow, but if suddenly you're walking and there's not many people in the way, you'll go fast. So if it goes fast, it's going to bend away from the normal. And we'd better just pop the normal in. And I get students asking, how much should I bend it away? Right. Well, imagine that this original ray kept going. It would come all the way over here. And you've got to make sure that these two lines are parallel, so they never touch. So when this bends, just say it bends by 10 degrees as it comes in. So say that that was 20 degrees and this is 10 degrees. Well, it's going to bend by 10 degrees back the other way. So that would be 10 degrees, and this one would be 20. And those angles are always like that, where that one there is the same as that one there, and that angle there is the same as that angle there. Well, I hope that's been useful. And as I say, it doesn't matter what exam board you're doing, they always have the same sort of 6-mark questions, the same sort of core practicals. Just make sure you know which core practical or which questions might pop up on your particular exam board, on each particular paper. Work hard, be nice, and bye for now.